Are you planning to build your own large language model from scratch? This is the course for you. Go through my previous lecture to set up the environment to build large language model from scratch. This session is introduction to large language model. What are we doing? What we are going to build? And we'll understand in this session what is a large language model. In this session, I'll cover large language models, definition of large language model, model size and parameters, transformer architecture, and the process of generating next token, how these models generate the next token. My name is Ram. So large language models, they understand, generate, and process human language at a massive scale. They're designed for sequence-to-sequence tasks like machine translation or generating tokens or generating text. Like you send the input text to the model and generate text. The large language model will generate the next token or the next text or new text based on the input text. That is output text. For example, if you send this prompt to the model, translate how are you into French, the large language model will translate this into reasonable French, properly reasonable French. For example, another prompt, if you send the model, what is the capital of France? You will expect the response from the model, the capital of France is Paris. Or write an essay on French Revolution. You can expect an essay on French Revolution from the model, like the title and the essay, complete essay. Model size and parameters, these are important in order to understand the model size and how the model size is calculated. Like this is a comparative analysis, not to be specific, like BART uses 3.7 billion tokens and 240 million parameters. So we use these terms, tokens and parameters, to understand the model size and the parameters. So first of all, model size. Model size is the memory required to store the model's parameter. And the parameters are tunable variables that are adjusted during the training to minimize the difference between predicted output or predicted tokens or predicted text and actual labels, means the correct answers. They are used to represent a relationship between the input token and the output text. What goes in and what model create. What is the relation between the input and the output? The parameters represent the relation. The goal is to find the optimal value so that the token generate accurately so that the model accurately predict new and unseen tokens or output. There are two types of parameters. One is learned embeddings, which are dense vectors that represent each token in a multi-dimensional space, fixed multi-dimensional space. There are learned embeddings capture semantic relationship between the tokens and are used as input feature for the model. Second is model weights. These are the adjustable values within the neural networks layer, like fully connected layer or convolutional network layers or recurrent layers. So these are important terms and definitions with respect to large language model. Large language model is by definition probabilistic model of text. For example, I wrote to the zoo to send me a pet. This is my first sentence. And they sent me, what will be the next token? There are many possible tokens or many possible words after this sentence. The large language model will predict the next token based on the probabilities. For example, the lion has a probability of 10%, elephant has a probability of 10%, similarly dog and cat and panther and alligator. So LLM gives a probability to each word in its vocabulary of appearing in the next space, that is next blank or the next token. By definition, large here refer to what? It refers to the number of parameters. And is there any threshold? No, there is no agreed upon threshold for the definition large. Understanding language for machines can be tricky. For example, if I have the sentence, Jane threw the frisbee and her dog fetched it. We know that Jane is doing the throwing, dog is doing the fetching, and the word it refers to frisbee. As human, we understand it easily, but for a machine, it can be very tricky. So understanding the transformer architecture, this sentence, Jane threw the frisbee and her dog fetched it, how it works in large language model, in the transformer architecture to be precise. Because all the models are built on transformer. At the core of the model is somewhere transformer working, which is a outcome of a research done by Google team, and the research paper was published in 2017, sorry. Paper was published in 2017, and the title of the research paper was Attention is All You Need. So the first process is tokenization, then embedding, then positional encoding, then that goes to the transformer, and at the end it uses softmax function to predict the next probable token based on their probabilities. So Jane threw the frisbee and her dog fetched it. How this process work, how the token is generated, let's try to understand this. The first process is tokenization. So the tokenization will break this sentence or the phrase into tokens, where each word or the punctuation mark will be a token. This is going to be our first lab, our first part of the building the model from scratch, where we will learn to build convert the text into tokens. So this is first step, tokenization. The sentence is broken down into smaller pieces called tokens. You can create your own tokens, your own function or your own class in Python or any other language to convert this text into tokens. We will be building this tokenizer from scratch using Python as our first lab assignment. That is our next session. So, however, the existing model, they use their own tokenizer, like GPT-2 uses the BPE tokenizer, byte pair encoding tokenizer. We'll understand byte pair also. We'll understand how the byte pair tokenizer work in one of the lab and one of the demonstration. The choice of how to break down the sentence depends on the specific tokenizer being used. So we'll be understanding how GPT-2 uses the tokenizer, how we can create our own tokenizer as well. So we'll go into that deeper of creating the tokens. Next is embedding. How these tokens, once converted to tokens, we convert embeddings for these tokens. So the tokens are converted to embeddings, represented as embeddings, like Jane is 2.1. In fact, this is not one floating point. The dot 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 represent, they are high dimensional. There may be let's say 1000 dimension, 1024 dimensions, or 1536 dimensions. By the way, the number which I'm using, 1024, is specific dimensionality of cohere embed model, and when I'm talking about 1536, that is the dimensionality of ChatGPT 3 based model, the small model for GPT-3 for embedding. 1024 or thousands of dimensions. Imagine the size of floating point numbers each word is represented as. So each word, each token is then converted to a numerical form, that is a vector that model can understand. That is also going to be our first lecture, where we'll understand the tokenization part. These vectors are created in a way that they capture the meaning of the word. Then positional encoding. The positional encoding layer represents the position of each word in the sentence, in the text which you pass, because model needs to know the order of words in the sentence. That is called positional encoding. The model adds information about the position of each word in the sentence, which means, for example, if Jane threw the frisbee and her dog fetched it, this is appearing at position 1, this is appearing at position 2, and so on and so forth. That is positional encoding. Now this token, their embeddings and the positional encoding, that goes to the transformer. And transformer have layers. There is multiple encoders which we will build in our lab, which in this course, that will have an encoder stack. This part represent encoder stack, this part represent decoder stack, And so imagine these words are processing and going through the encoder stack, and this same text, whatever the input is, that goes to the decoder stack also. There are multiple decoders, but look at, pay special attention to this red line which is pointing to this dog. Actually, basically this concept is paying attention. When you are looking for word Jane, we are paying attention to all other words. What am I trying to say is, when I'm talking about dog in the decoder stack, I'm paying attention to the tokens, which are other tokens which are there in the encoder stack. So pay attention, or attention mechanism, is the core, is the key idea of this large language model, of the transformer architecture of the large language model. We'll build our own attention mechanism while building the large language model from scratch. So attention help understanding the context of each word. In fact, there's a very important term called Q, K, and V. This attention is a pure mathematical concept, which I will explain when we'll be building our model. Q means query, K means key, V means value. Query, key, and value. Three important points here, Q, K, V, which actually helps in understanding the concept of attention. Then forward, the feed forward applies a specific function to each word individually, and that is the feed forward layer. So we have attention, then feed forward. Model generate a list of scores for each word in the vocabulary, that use softmax function. It uses softmax function to turn these scores into probabilities. Actually, it's again a mathematical function. How the softmax function is applied, we'll understand that also while building the model. This presentation demonstrate or explain the whole concept of building the large language model from scratch, and we'll be building each of these components thoroughly from ground up. So who threw the frisbee? If that is our text, the first part is tokenization, then embeddings, then positional encoding, that goes to the transformer. Output from the transformer goes to the linear layer, then softmax function, and answer is Jane. The output from transformer softmax layer is the probability distribution across the entire dictionary of words. The model realizes that Jane is associated with the action of throwing the frisbee, and that's how the next token is generated. The model predicts the next word given the context, who threw the frisbee, and the answer is Jane. That is how the transformer works. Subscribe to this channel for the complete course on building large language model from scratch, and I'm sure you will be able to build your own model at the end of the course. Thank you so much. Bye bye.